Okay, hope everybody had a good spring break. So we're going to continue our discussion of convolutional neural networks. So last time, just before the break, we talked about convolution. So let me just kind of review what that was. So the idea is based on pattern matching. You have a large image, and you're looking for a particular pattern, like you're looking for this, something like this number 4, which we call the kernel. And so what you do is you take that little image and you slide it around within the big image. And once that template is on top of something, wherever you slide that, you take a pointwise multiply of the pixels in that kernel and the pixels in the image, and you sum them up. So the idea is when that kernel or template is on top of something with a similar shape, you're going to get a big output. But if you move that template so it's sitting over here and you're multiplying it with an input with very different or very little brightness, you're going to get a small output. So by moving that template all through this image, you're going to construct a new image that's going to have, brightness values more bright where there are things like that template. So that's the idea behind convolution. This is the equation that implements it. So here's the larger image. This is the kernel. This is a sum over all the pixels in the kernel. And you can see that those are offsets to the output pixel index pair here in this image. So that's the idea behind. And actually, this is called correlation officially. Not technically convolution, but correlation. Okay, any questions on this? Okay. And then we said that if you take that idea and you put some minuses here, which you can think of as equivalently flipping and reversing the kernel, then you get what is known as convolution. And so the difference between them is really just whether you flip and reverse this kernel or not. And essentially, the way we're going to use this is we are going to learn the kernel. And so we could use either of these. If we use this, we would learn one kernel. If we use this, we would learn a flipped and reversed version of that same kernel. So because this one is a little bit simpler than having the minuses there, this is what's used in machine learning. And they call it convolution, even though technically it would be correlation. Okay, so is that making sense? All right, so, and then the other thing we talked about was how do you handle the edge conditions? So when you move your kernel around in your larger image, the question is whether you always keep it inside or whether you allow it to go outside the larger image. And when you do that, you're essentially assuming that there are zeros there. And here's a case where you allow it to go out of this image as much as possible. And the difference that you see in the size of the outputs is that, for example, here there's only 4 possible shifts of that kernel, so your output image is 2 by 2. At this extreme, the output image is actually bigger, more pixels than the input image. And in this same mode, which is the most popular one, you use just enough zero padding so that the output and input images are the same dimensions. And that's pretty convenient. For example, if you start with an image that has nice round numbers like 256 by 256, and you use same padding, then you continue getting those nice numbers through your processing stages. But these are all options that are available in the software. Yes?
My doubt is in actually in the previous slide. I did not quite understand the difference between correlation and correlation.
So,
what difference does it make during the computation?
So yeah, the math, in terms of the math, the difference is whether there's a plus or minus here. The way that I like to think about it is if you take this expression and you do a variable substitution where you change the sign on the k's and you get some new k's that have a different sign, you can basically move the signs of the k's over here. And so now this tells you that these two are like the same, except that essentially this uses a flipped and reversed version of the kernel.
But the computation looks similar. Is it like the elements of the kernel is multiplied with the decimal values of the images?
Yeah, that's what's happening here. You can see the multiplication.
Yeah. And then what difference does it make, the plus and the minus?
It's just a matter of whether the kernel is flipped and reversed or not.
So it's basically learning two kernels.
No, you either do this operation or you do this operation, one or the other. And so I'm just telling you this as background. This operation is called correlation. This operation is called convolution. But if I'm going to learn the kernel, then if I do this, I'll learn one kernel. If I do this, I would learn a different kernel.
Yeah.
But if I would look at the kernels, I would notice that the kernel learned here is just going to be a flipped and reversed kernel, flipped and reversed version of this kernel.
Yeah.
So that means that there's really no advantage in doing one or the other. I mean, I would learn the same kernel in the end. I would have everything the same. The only maybe advantage is that this minus sign is a little bit less convenient in terms of the math. So this is what's used in practice. Okay, so all right, so we have convolution. Any questions on convolution so far? Okay, so we looked at some examples. We took this original image and we used a kernel that was, it's a 9x9 kernel, and all the entries in the kernel are identical. They're the numbers 1 over 81. That means if you sum the kernel up, you get the value 1. And we moved that 9x9 kernel around this image, and depending on the zero padding mode, whether it was full, same, or valid, we got these images. And here you can see that when you use that full zero padding, that means you've added a lot of zeros on the edge of this image before convolution, and then you see the effect as this kind of dark border region. And if you zoom in, you can see it more clearly. With the valid convolution, there is no darkness at all. And with the same, there is a little bit of darkness, but you do have the advantage that the input and output sizes are exactly the same here. And then the other thing you see happening is the original sky was a little bit noisy, wasn't a, uniform gray, but after you do this convolution, it has an averaging effect where it basically averages all the pixels in the window, which gives you this very uniform gray color here. So this kind of a kernel is a sort of crude way of doing what we call denoising, which is removing some random noise from the pixels. But it comes at a cost of blurring the image, as you can see here. The image gets blurry as a result of that convolution. So it's not the most sophisticated way to do denoising. Okay. All right, any questions? Okay. We also played with different kernel sizes, same uniform weights. So we find as the kernel gets bigger, the images get even more blurred. We also looked at non-uniform kernels. This is a Gaussian blur kernel, which is kind of like a Gaussian hump in both directions. And you can see it also does blurring, but maybe not quite as much blurring as the equivalently sized uniform kernel. And finally, we looked at these Sobel filters, which are, they have this sort of roughly Gaussian shape in one dimension, but in the other dimension, they have positive, 0, negative, which means that this one is good at detecting edges that are vertical edges, and this one is good at detecting horizontal edges. And when we applied them, here you can see we're detecting the vertical edges. So whenever we have a light to dark going edge, we get a white here, and if we have a dark to light going edge, we get dark. And then here we have the same for horizontal edges. Okay, so just some illustrations of the sort of things you can do with convolution. Of course, you can do a lot more if you make the kernels more interesting. Okay, so moving on to today's discussion, we're going to be talking about the overall structure of these convolutional neural networks. So this is this AlexNet. We said this was the one that sort of started the deep network revolution back in 2012 with the ImageNet competition. And so let's just talk sort of at a high level about the structure. So you can think of as the network architecture as having layers, very similar to what we talked about with the multi-layer perceptrons. So within each one of these layers, you can say that there's three operations. There's this linear operation, which is based on 2D convolution. Then there's a nonlinear operation like ReLU activation, same as what we saw with the MLPs. And then as a new concept, something called subsampling or pooling. I'll describe that in just a moment. So here we have like one of those layers would be represented there, and then the next such layer would be like that, another one, another one, another one. And what you see as you go through the network, you start with an input that you can see is a 224 by 224 pixel 3-channel image. That's because it's a color image with red, green, blue channels. So this blue box is depicting the data that we have coming into the network. This kind of pyramidal thing is used to illustrate convolution. So this is taking an 11 by 11 kernel, and it is shifting that around through all those spatial locations. But actually, it's not just one kernel. What we have here in the first layer, we said we have 3 channels, but in the next stage of the network, we actually have 96 channels. And in order to get, let's say, the first pixel in the first channel here, what we actually did was used 3 separate kernels, one for each one of those channels, and we summed their outputs. Okay, so for each one of these 96 channels, we have 3 kernels. That means in total, we have 3 times 96 different kernels to learn and to use in this layer. We'll be talking a little bit more about the details of this multi-channel convolution thing in a few slides, but that's basically what's happening. Okay, so that same operation is happening over and over, except now you can see we go from 96 channels to 256 channels, 256 to 384, and so on. And we do this for, it looks like 1, 2, 3, 4, 5 layers. And then we change the operation of the architecture to basically an MLP. So this last part is exactly what we talked about in the last unit, except this might have more than 2 layers. As you can see, this has 3 layers. And so here, essentially, okay, so to go from this left to the right half of the processing architecture, you take this cube of data and you just vectorize it into a single vector of dimension 256 by 13 by 13. From there, you do a little bit more subsampling to get it down to 4096. And now you're going to have a 4096 input vector here that's going to go through a 4096 by 4096 matrix, followed by some ReLUs to get to here. That's like one layer of the MLP. And then another 4096 by 4096 matrix to get to here. Again, some ReLUs. And then finally, you're going to put it through a 4096 to 1000 matrix to get your final output, which is a vector of 1000 elements. Does Does anybody remember why the final output has 1,000 elements? That's the number of classes, exactly. So from a high level, you can see that at the beginning of our network, we have purely spatial data. We have data, well, I guess you could say there's 3 channels, but almost purely spatial. We have 224 squared pixels. At the end, we basically have a single pixel, but we need 1,000 channels. Each channel will represent the confidence in a particular class. So as our data flows through the network, we need to gradually transform from many pixels and just a few channels to many channels and just a few pixels, in particular 1. And that is kind of why we keep growing the dimension 396, 256, 384. We're growing the number of channels while reducing the pixel size. And this reduction of pixel size from 224 by 224 to 55 by 55 and so on, that is what we use these sorts of operations for, which we'll talk about in a moment. Okay, so that's sort of the architecture at a high level. We'll go through these different, well, I guess we talked about, we'll go through these different stages in the next few slides. Are there any kind of big picture questions before we dive into the details? Okay. So let's first take a step back and talk about tensors. So tensor is just a fancy word for a multi-dimensional array. So we've been working with many kinds of tensors already. So anytime you have a matrix or a grayscale image, that is basically a tensor with 2 dimensions. And if you want to look at the shape of the tensor, you would say that it's this image would be a matrix where you would have the height of the number, the dimensions would be height and width of the image. Now, if I have a color image, then I have a 3-dimensional tensor, and the dimensions or the shape of that would be height, width, and maybe I should write number of channels. And here the idea is we're talking about RGB images, so we have the red channel, the green channel, and the blue channel. Now, as we know, when we want to run gradient descent, and in particular stochastic gradient descent, to learn things, we want to work with mini batches. So not just a single image, we want to work with a number of images, maybe 128 or however many we can handle. And so now, in that case, the tensor has 4 dimensions. So the first dimension would be however many elements are in a batch. That would be the size of it. And then the remaining dimensions are just for color images. Okay. So that's examples of tensors, and in particular the most important tensors that we'll see going forward. Any questions on these? Now, different frameworks or libraries will want to see the data arranged in different ways. And if it's not arranged in the way that it expects, it will do the wrong thing. So notice here, when we talk about color images, I'm saying that the first 2 dimensions are height and width, and the last dimension is channel. But that is actually, that's true for skimage, that library, but it is not true for PyTorch. PyTorch wants you to do it in a different way. First of all, PyTorch wants you to always work with mini batches. And even if you're working with a single image, that's fine. You just have your mini batch dimension equal 1. But it needs to be a 4-dimensional tensor. You would just have 1 as the size here. And notice how it does things. It does index, channel, height, width. So here, in order to, if you start with skimage and you want to go to PyTorch, you actually have to shuffle your data such that this channel is moved to the front. It's kind of like a matrix transpose, but it's a generalization of a matrix transpose to tensors where you're shuffling around the elements across dimensions. So we'll see some examples of this when we look at the code, going back and forth. Okay, any questions on these tensors? Okay, And just in terminology, so the number of dimensions, sometimes people refer to it as the degree or the order or the rank. And what's a bit confusing is that the word rank for matrices has a totally different meaning. As we know, it's like the number of linearly independent columns in a matrix. But when you talk about the rank of a tensor, you're really just talking about like how many dimensions it has. And then the shape of a tensor is a list of numbers that tells you exactly what those dimensions are. So if you had, a data cube that was 10 by 20 by 4, then it would be a tensor with degree 3 and shape 10, 24. So those are just some terminology. And you've been working with tensors already. In NumPy, they're ND arrays, and in PyTorch, they're torch tensors. Okay, so any questions? Okay, great. So now we can talk about convolutional layers. And so this is sort of a generalization of what we talked about before, where now we have different batch elements and different channels. So it turns out that the batch element aspect is pretty easy because you just process every batch separately and in parallel. So as you can see, this is the output of the convolution layer. This has the same structure as we would expect for, this is the input tensor shape. So number of elements in the batch, number of channels at the input, number of vertical and horizontal pixels. So that's the input tensor, that's here. This is the output tensor. So whatever happens for the first batch element, the batch index is just seen here and here. So basically it's like that the different batch elements are processed identically and separately. Okay, then if you just focus on these parts, this is the convolution equation you saw previously. Forget about this. So here you can see these are the output pixels. These are the kernel pixel indices, and here are the outputs plus the offset. So this is exactly the convolution we saw before. So what's new is that now there can be multiple channels. So here is the channel index at the input, which we call N. The channel index at the output is called M. And you can see that there's a separate kernel for each combination of M and N. So for each input channel and each output channel, there's some kernel connecting them. And then the other thing that happens at the channel layer, I'll just highlight the channel stuff, is it's a summation across the input channels. If you think about it, this is exactly matrix multiply. So if you just had single pixel images, single pixel kernels, you're just doing a matrix multiply across the channels. Okay, so in total, you have a combination of matrix multiply across channels and then convolution spatially. So maybe I'll come back to this over here. So again, for every combination of one of these channels and one of those channels, you have one 11 by 11 kernel. And if I want to ask the question, how do I build the output here in this channel? I would basically be summing the kernel outputs for each of those three input channels to get to this output channel here. So in total, I need 3 times 96 different real valued kernels. Okay. So a little bit of stuff going on there. Are there any questions about this? Is this making sense, or is this just hopelessly complicated? So this part is some cross input channels. This part is like separate batch processing here and here. And then we have basically convolution, spatial convolution. Yes? Yeah, I was going to talk about that next. Okay, so in addition to this, it's kind of like a, it's like a, kind of like a matrix multiply, but with the convolution structure. We also have a bias term. So remember in our MLPs, we just had a plain matrix multiply, but then we added a bias. Well, here's our bias. And as you can see, for every output channel M, we have a single scalar bias. That means all the pixels in the output channel are shifted by that same scalar. Okay, so one bias for the entire image. Of course, you're going to have a bunch of images. C out different images, so you're going to have C out different scalar bias coefficients. Okay. Are we good with this, or does anybody have some more? Yes.
I have also another general question.
Sure.
You might answer it later. But how do you decide on the output channel over all of the dimensions?
Oh, that's a great question. Yeah, how do we decide that? There is no correct answer. It is it's sort of, people do this with a combination of intuition and trial and error. So on one hand, because there's no equations that will tell you what are the optimal set of channel sizes. So some of the intuitions that we have is that if you have too few, it's very similar to the MLPs when we discussed how do you choose the number of hidden layer neurons. So now the choice we make is essentially the channel widths. So if I make these too wide, then I have a lot of neurons on my network. I have a lot of I have issues with memory, with processing speed, those sorts of things. If I make them too narrow, then I maybe don't have a powerful enough network to really describe what I need to do classification well. So as you can see, yeah, if you looked at the total number of pixels in this data structure, I don't exactly know what it is, but you could maybe plot it across these stages, and you would see it would sort of grow. It would grow to a height in the middle, and then it would shrink back to 1,000. So these guys, they tweaked all those numbers. I don't know what they chose, in their set of possibilities, but they finally came out with this.
So there's no straightforward way to decide on all of this type of problems?
There's no single method that everyone uses.
Do they always throw the dense layers on the end, like when they do the classification of it? Or?
Yeah, so we'll talk about more of this later, but basically, one of the nice things about convolution is that it can handle any sizes here. So if I make this image twice as big, I can still use exactly the same kernels. I'll just get this image twice as big. So this architecture can handle images of different sizes. But at the end, I have 1,000 classes, right? And only 1,000 and always 1,000 classes. So somewhere we need a way of converting this part of the network that is able to handle different sizes with this part of the network that is sort of designed for a fixed number of output classes. And so there's a little processing layer in here called average pooling that makes sure that it subsamples this in just the right way to have exactly 4096. So, but yeah, the goal of this, you could say, is to get some features that work well at the beginning of this MLP. And we'll also talk about, like, once you train this thing, you can actually use this part for all sorts of other tasks, even if you're not doing classification. You could use this, it's used for a whole bunch of other things we'll talk about. So the early networks were designed like this. Later on, they actually started to get rid of these dense layers, and they just had the average pooling at the last convolutional layer, and then they just made sure it had 1,000 classes that way. So, over time, people's understanding of what was best changed as they played with things, and so this is just how the first networks were built. They had convolutional followed by dense. Okay, great. Any other questions? Okay, so we talked about tensors, talked about convolutional layers. Now let's talk about how we change the sizes of the image. So generally speaking, I'm calling this pixel pruning. And again, the reason we need to do this is because we want to gradually change from 224 by 224 by 3 to 1 by 1,000. And so we can do that by growing the channels gradually and shrinking the spatial dimensions. So when we shrink spatial dimensions, roughly speaking, we shrink by a factor of 2 or 4 usually. If you look at these numbers like 55 to 27, that's roughly a reduction in 2. 27 to 13, again, reduction by 2. And 224 to 55 is roughly shrink by 4 in each dimension. So how do we do that shrinking? There's basically 3 common options: subsampling, max pooling, or average pooling. So what subsampling does is perhaps the simplest. Let's say that I have this image, and I want to reduce the dimensionality by 2 in each direction. What I would do is in this top left corner, if I'm doing subsampling, I just keep this element, this element, this element, and this element, throw away the other elements, and now I've shrunk from 4 by 4 to 2 by 2. So that's what subsampling does. It's the simplest. If you've taken a course like 5200, exactly the same thing. It's called downsampling, signal processing. The size of the region over which you let's see. Yeah, so S by S is the region over which you take the top left pixel. That's called the stride. So in this picture, the stride would be like 2, because we're just taking 1 pixel from each S by S. And then the other thing is that actually subsampling is not implemented after convolution, but it's implemented together with convolution. Because if you know you're going to take these pixels, then there's no point in ever computing these other ones. It would be wasteful. So when you do convolution with stride, it only computes these. It doesn't compute any others. And in signal processing, that's called polyphase methods, polyphase downsampling. Okay, so that's subsampling. Any questions on that? Okay, so max pooling, what you do is you have the same notion of stride. You're shifting around a certain region by S horizontally and vertically. But actually that region could be bigger than S by S. It could be a K by K region where K is bigger than S. And rather than keeping the top left, you keep the largest value in the region. So here's another illustration. So here's the input. Let's say that I have this K by K region is 2 by 2. So I look for the largest pixel value here. It turns out to be 5. So that is the number that I keep. Then I shift over my window here, look for the largest. That happens to be 4. I shift it over here, largest is 4, and so on. So that would be the case where this K is like 2 by 2, and it's shifting by 2. Oops. Here. But here's an example where I have a 3 by 3 region, and I'm shifting that over by 2. So I'm getting the same amount of subsampling because S is 2, but I'm looking over a larger region to compute the max. So those are two options with max pooling. Any questions on max pooling? Okay. And finally, average pooling is exactly like max pooling, but you take the average instead of the max. So here, you just average those 4 pixels and store that number. You would average those 4 pixels, store that number, and so on. Okay. So those are the most common ways that people shrink the images or the feature maps as they go through the network. This is done independently on every channel and every batch item. Okay. Any questions? Making sense? Okay. Good. And dense layers. Dense layers are basically familiar to us because this is exactly what we used for multi-layer perceptrons. The only thing is to discuss some details. So let's say that the last convolutional layer, after we're done pooling, gave us a tensor of this size. So we have B items in our batch, C out channels, N1 by N2 pixels. So what we're going to do is to get this, to prepare it for the first dense layer, we're going to flatten it or reshape it reshape like this three-way tensor into a vector. Or reshape this four-way tensor into this matrix. So basically, we're just like, flattening, unraveling all those pixels into NN, to a vector of length NN. So NN is just the product of all those dimensions. And now that we have vectorized it, we can just essentially put that vector through our matrix multiply. And we do this for every different element in our batch, just like before. So independently on every batch element, we do a matrix multiply, just like we did in our MLPs. Okay. And in a very special case of convolutional layers, if you have a convolutional layer where your kernels are 1 by 1, so they're not very interesting, and if you had images of dimension 1 by 1, so a single pixel, then basically that's what these layers are doing. It's like a very, very simple version of convolution. So the nice thing is that means that if I do a derivation for convolutional layers, it also works for dense layers because dense layers are just a special case of convolutional layers. So when we do backpropagation, we'll derive backpropagation for these convolutional layers. Our derivations will also hold for dense layers. Okay, so any questions on the dense layers? Great. So why are we doing convolution then? Okay, hopefully this is convincing. Basically, convolution dramatically decreases the number of parameters that we need to learn. So let's look at some examples from AlexNet. So let's say that the input to a convolutional layer is a tensor of this shape, and the output is a tensor of this shape. So that means we're using same mode because we have the same number of pixels. And if you look at the second layer in AlexNet, essentially this is what we have. We have 55 by 55 pixels, 96 channels on the input, 256 channels on the output. And we don't need to really worry about the batch dimension because we're going to be doing this for every batch element separately. Okay, so that's the setup. So if I have a convolutional layer, then what we said is the number of weights in my kernels is for every combination of input and output channels, I need a kernel of size k by k. And in AlexNet second layer, they use 5 by 5 kernels. And if you take 96 by 256 times 5 times 5, you get 600,000 weights. It sounds like a lot, but as we'll see, it's nowhere near what we would get if we tried to do this with a dense layer. In terms of how many bias coefficients, it's just however many output channels we have, which is 256. Now let's say that I want to try to go from this tensor to this tensor using a dense layer, dense linear layer. So if we think about it, you can sort of draw it as a matrix. So I would need to flatten my input. So this would basically, okay. So I would have here, this is the matrix W that I would need to use. The dimension, the number of columns is going to be Cn times N1 times N2, and the number of rows is Cout times N1 times N2. And so when I look at the total number of coefficients in the matrix that I need to learn, it's this dimension times this dimension, which is Cout, Cn, N1 squared, N2 squared. And if you plug in these numbers, you get almost 1 trillion weights. Okay, so we've gone, if you look at the number of weights required for convolution to the number of weights required for fully connected or dense, it's about a factor of 1 million growth. So we save a factor of 1 million by doing convolution versus fully connected. In fact, there's no way you could do fully connected. It would just be impossible. Couldn't fit that on any computer. It's too many. And this is just one layer of the network, right? There's actually a bunch of these. So convolution is really what allows us to do image processing at scale. So it's a massive simplification. So you might then ask, well, what do we lose? It's nowhere near as expressive as a full matrix multiply. In fact, convolution, you can kind of think about it, if you're in one dimension and you want to say, what does a convolutional matrix look like in one dimension? It has a toplet structure. All the diagonals are the same. And whatever your kernel width is, that would be like some non-zero elements here. And then essentially you would have zeros elsewhere. And so that's nowhere near as expressive as a full matrix that can put coefficients everywhere. So it's weaker, but it's basically powerful enough. It does have this translation invariant property, which we want, meaning it can look for these patterns anywhere in the image. When you look at what happens, what the kernels we learn in the early stage of the network, we learn some very nice, simple, generic patterns. But at later stages, convolution is used to basically make very sophisticated inference about our data. Now, it's still not the right thing for all applications. Like if you're doing text processing, if you're building a large language model, convolution doesn't really work because convolution it has this spatial invariance, but if I'm working with words in a sentence, the order of the words matter, the location matters, and so I can't just use convolution. And so this is why in large language models, they do not use convolutional neural networks. They use things called transformers. And transformers have much more the flavor of matrix multiplies, and their complexity is also much greater than convolution. So we won't be getting into that in this course, but I just wanted to say that convolution is like the key idea for image processing, but it doesn't work with all types of data. It doesn't work that well for language data. It's just a caveat. Okay, all right. Any questions on convolution? Everybody good? Okay. Let's look at a little bit of the code of how do we do some of this processing in scikit-learn and PyTorch. So previously we did this edge detection. We looked at edge detection. We used scikit-learn. Let's see how we can do this with PyTorch. So what we start with is an image, grayscale image. It's just basically a matrix with n rows and n columns. So the first thing we need to do is convert that to the right shape to work with PyTorch. And remember, with PyTorch, we need a four-way tensor where we have the first dimension is the number of images in the batch. Second is however many channels we have, and then how many rows in our image, how many columns in our image. Since we're just working with a single image, number of images in our batch will be 1. And since this is a grayscale image, number of channels on the input will also be 1. Okay, so basically we're going to, we create this batch shape, which is just a tuple of 4 integers, 1, 1, and whatever, I guess 256 by 256. And we just do im.reshape into that batch shape. And this is actually not yet in, this is just in NumPy. This is not yet in PyTorch. Here's where we go to PyTorch. We take that NumPy-X, which has the right shape, and we cast it as a torch tensor. And now this thing can work with PyTorch. And torch, some of the syntax is a little differently. Like in NumPy, you would do .shape to see its shape. In PyTorch, you do .size to see its shape. But you can see that this is the shape here. 1, 1, 512, 512. Yeah, actually this is 512 by 512, not 256 by 256. Okay, so we've got this image into PyTorch. Okay, how do we build our kernels? So we can start in NumPy, make a NumPy array, and we're just manually making these kernels because they're so small. It's just easy enough to do this. We make a 3 by 3 matrix of this and another 3 by 3 matrix of this. Okay, so now coming back to PyTorch, let's create a model that's just a single convolutional 2D layer. So here we have to instantiate it, we have to say how many input channels will there be? 1. How many output channels? 2. Because when we go through this layer, we're going to output both the horizontal and vertical edges. So 2 channels at the output. And the kernel size is going to be 3 by 3, which is basically the shape of this. Okay, so how do we load these filters into this PyTorch object? What we can do is we can extract the state dictionary. So we take our model, do state dictionary. This gives us our state dictionary. And we can look inside, and we could extract, if you wanted to see the randomly initialized weights. When we instantiate this, they put small random numbers for W and B. You could print them out if you want. But here, we're just creating these variables that essentially gives us the right size. And then we're going to insert the coefficients from above. So this is going to be if you remember the way that this tensor is organized, it's the number of output channels, number input channels. So there's only one input channel, so both of these have zeros. And this is either the first or the second output channel. And then the rest of the terms are from WX for the first one or for WY for the second. We don't need any bias coefficients, so we're going to set those to zeros. Now that we have updated B and W, we put them back into the bias and weights using the state dictionary, and we load the state dictionary back into the model. And now all we have to do is take our XTorch, put it through our model, and out comes those edge maps. This is in PyTorch. If we want to plot it in matplotlib, we need to bring it back to NumPy. But you can see we get exactly the images that we had before when we did everything using scikit image. And it's actually the same as the correlate. Remember, not the convolution, but the correlation from SciPy signal. Okay, so that's pretty simple example. Everybody good with what we did here? Any questions? Let's do something a little bit more sophisticated with color filtering. So here what we want to do is you want to start with this color image, and I want to build 4 little color filters that essentially give me a heat map of where the most red I see, where's the most green, where's the most blue, where's the most pink. So the idea is I make a little kernel, and I'm calling this a red kernel. Actually, this is really 3 channels. Like if I plot a color image to us humans, you have to think, well, there's actually really 3 channels behind that. There's a red channel, a blue channel, and a green channel. So really this little picture of a kernel is really 3 kernels. There's like 3 real value kernels, one that says like the red coefficients of the kernel, the green, the blue. Okay, so that's what I want to do. If I want to take this guy, slide this around, and I expect that wherever it has the most red, like where this red apple is, that's where I would get the brightest output from that kernel. Does that make sense, sort of the goal? I'll give you a sneak peek what happens. So this is what you get. It's a little bit non-intuitive, maybe because you thought apples are always red. Well, actually this orange has more red than the apple. But this is what you get for that kernel once sliding around. You see, this is where most of this color is in the image. And like the background has almost none of that, so it's totally black. And for green, we're going to get this. This is going to pick up the green apples. Blue is going to pick up, actually this has the most blue in it, and so on. Okay, so if the goal is clear, we could get back to how we actually do this. Everybody go to the goal? Okay. So basically, how many output channels do we expect to get then? 4, right? 1 output channel for each of these, and each of those output channels will be a full image. So basically, like this is going to be specify 3 of our kernels, 3 more, 3 more, and 3 more. So really there's like 12 real valued kernels here. Let me see. I think this is probably a good time to stop. We can dive into the details next time, but yeah, now that you see kind of what the goal is, it's a good time to stop. All right, see you guys on Wednesday.